Good morning, everyone. Now we will proceed through the next chapter. In our next chapter is thermodynamics. So let's start. General introduction. It is a well-known fact that most of the physical changes and chemical changes are accompanied energy changes. These energy changes may take place in the form of heat, light, work, electrical energy, etc. All these forms of energy are convertible into one another and hence are related to each other quantitatively. The branch of science which deals with the study of different forms of energy and thus quantitative relationship between them is known as thermodynamics. When we confine our study to chemical changes and chemical substances only, the restricted of thermodynamics is known as chemical thermodynamics. The complete study of thermodynamics is based on the generalization called first, second, or third law of thermodynamics. These laws of thermodynamics apply only where the system is in equilibrium or moves from one equilibrium state to another equilibrium state. The laws has been arrived at put on the basis of human experiences and there is no theoretical proof of any of these laws. However, the validity of these laws is supported by the fact that nothing contrary to these laws have been found so far and contrary to expected. The importance of thermodynamics lies in the following fact. First, it helps to predict whether a chemical reaction can occur under the given set of conditions. Second, it's help in predicting the extent of reaction before the equilibrium is attained. Third, it helps to deduce some important laws like law of chemical equilibrium, distribution law, the limitation of thermodynamics. It helps to predict the feasibility of a process but does not tell anything about the rate at which reaction takes place. It deals only with the initial and final states of a system but not tell anything about the mechanism of the process. It deals with the properties like temperature, pressure, etc. of the matter in bulk but does not tell anything about the individual atom and molecule. Some basic terms and concepts. First, system and surrounding. The part of the universe which is chosen for thermodynamic consideration is called a system. The remaining portion of the universe, excluding the system, is called surrounding. So, universe is equals to system plus surrounding. However, as the entire is not affected by the change takes place in the system, therefore, for practical purposes, the region of space in the neighborhood of the system is taken as surrounding. A system usually consists of a definite amount of one or more substance and is separated from the surrounding by real or imaginary boundary through which matter and energy can flow the system of the surrounding or vice versa. Open, closed and isolated system. First, open system. A system is said to be open system if it can exchange both matter and energy with the surrounding. For example, if some water is kept in an open vessel or if some reaction is allowed to take place in an open vessel. Animals and plants are open systems from the thermodynamics point of view. Second is a closed system. If a system can exchange only energy with the surrounding but not matter, it is called a closed system. For example, if some water is placed in a closed metallic vessel or if the reaction is allowed to take place in the cylindrical enclosed by piston then as in vessel. Closed. No exchange of matter between the system and surrounding takes place. However, vessel has conducting walls, exchange of energy can take place between the system and the surrounding. Third is isolated system. If a system can neither exchange matter nor energy with the surrounding is called isolated system. For example, if water is placed in a vessel which is closed as well as insulated, no exchange of matter or energy can take place between the system and the surrounding. This constitutes an isolated system. Tea placed in thermos flask is an example of an isolated system, whereas tea placed in a closed steel teapot is an example of closed system, and tea placed in an open cup is an example of open system. Third, state of a system and state variables. The state of system means the conditions of the system which is described in terms of observable properties such as temperature, pressure, volume, etc. of the system. If any of the properties of this system, the system is said to be in different state. That is the state of system changes. That's why these properties of a system are called state variables. A process is said to occur when the state of the system changes. The first and last state of a system are called the initial and the final state, respectively. Fourth is state function. A physical quantity is said to be a state function if its value does not depend upon the state of a system, depends upon the state of a system, does not depend upon the path by which the reaction has been attained. For example, a person standing on the roof of a five-storied building has a fixed variable potential energy irrespective of any of the fact whether he reached there by stairs or by lift. Examples of physical quantities which are state function include pressure, volume, energy, enthalpy, entropy, free energy, etc. Volume is a state function because, for example, change in volume in water in pond is independent of the route by which the water is filled, that is by rain or tubal or by both. Fifth is macroscopic system and macroscopic properties. System contains a large number of chemical species, that is atom, ions or molecules. It is called a macroscopic system. The word macroscopic implies large quantities. Thermodynamics does not deal with the properties of individual atoms and molecules but deals with the matter in bulk. Such properties of the macroscopic systems like temperature, pressure, volume, density, melting point, boiling point, etc. are called macroscopic properties or thermodynamics properties. These are further classified into two types. First, extensive properties. These are those properties which depend upon the quantity of the matter contained in the system. The common examples of these properties are mass, volume, and heat capacity. Besides these, some properties discussed later in the unit include internal energy, enthalpy, entropy gives free energy, etc. Next, second is extensive property. These are those properties which depend only upon the nature of the substance and are independent of the amount of the substance present in the system. The common examples of these properties are temperature, pressure, refractive index, viscosity, density, surface tension, freezing point, etc. It is because pressure and temperature are intensive property independent of the quantity of the matter present in the system that they are frequently such used as variables to describe the state of a system. It is interesting to note that an extensive property may become intensive property by specifying units amount of the substance contained. Thus, mass and volume are extensive properties, but density and specific volume are intensive of the system, of the substance or the system. So, similarly, heat capacity is an extensive property, but specific heat is an intensive property. In general, ratio of two extensive property is always intensive. Next is thermodynamic equilibrium. A system is said to be in thermodynamic equilibrium if its macroscopic properties like temperature, pressure, etc. do not change with time. Thermodynamic process. A thermodynamic process is said to occur when the system changes from one state to another. The different processes commonly met with the study of chemical thermodynamics are as follows. First, isothermal process. When a process is carried out in such a manner that the temperature remains constant throughout the process, it is called an isothermal process. Obviously, when such a process occurs, heat can flow from the system to surrounding and vice versa in order to keep the temperature of the system constant. Second is adiabatic process. When a process is carried out in such a manner that no heat can flow from one system to the surrounding or vice versa, that is the system is completely insulated from the surrounding, it is an adiabatic process. Third is isochoric process. It is a process during which the volume of the system is kept constant. Last process is isobaric process, sorry. It is a process during which the pressure of the system remains constant. Next is reversible and irreversible processes. The various types of processes mentioned above are carried out reversibly and irreversibly. These terms may be understood as follows. In order to understand a reversible process, imagine a gas confined within a cylinder provided with a frictionless piston upon which is spilled some very fine sand. Suppose the pressure exerted by the gas on the piston is equal to the combined pressure exerted by the weight of the piston, the pile of sand, and the atmospheric pressure. Under these conditions, the piston does not move at all, and the state of equilibrium is said to exist. Now, if one particle of sand is removed, then the gas will expand very slightly, but the equilibrium will be restored almost immediately. Such a change is called infinitesimal change. If the particle of sand is replaced, the gas will return to its original volume. By continued removal of particle of gas, the gas can be allowed to undergo a finite expansion, but each step in this expansion is an infinitesimal and can be reversed by infinitesimal change in the external energy. Thus, a reversible process is a process which is carried out infinitely times slowly so that all changes occurring in a direct process can be exactly reversed and the system remains almost in one state of equilibrium with the surrounding at every stage of the equilibrium. Now here are the main point of differences between reversible and irreversible. Reversible, the process is carried out infinitesimally slowly that the difference between the driving force and the opposite force is very low. Irreversible, the process is not carried out infinitesimally slowly but it is carried out rapidly. Reversible process, at any stage during the process equilibrium is not disturbed. Irreversible process, equilibrium may exist only after the completion of the process. It takes finite time for completion. Reversible, while it takes infinite time for completion of irreversible. Reversible process, it is only imaginary and cannot be achieved in actual practice. Irreversible process, these processes actually occur in nature. And reversible process, work obtained is maximum, and in irreversible process, work obtained in this process is not the maximum. Now, here are some thermodynamic quantities also. A is internal energy. It has already been mentioned that whenever some process occurs, it is usually accompanied by some energy changes. The energy may appear in the different forms such as heat, light, work, etc. The evolution of or absorption of energy in different processes clearly show that every substance must be associated with some definite amount of energy, the actual value of which depends upon the nature of the substance and the conditions of the temperature, pressure, volume, and composition. It is the sum of different types of energy associated with atoms and molecules such as energy, electronic energy EE, nuclear energy EN, chemical bond energy EC, potential energy EP, and electrical kinetic energy EK, which is further the sum of translation energy ET, vibrational energy EV, and rotational energy ER. It is usually represented by symbol U or E. Thus, U or E is equals to EE plus EN plus EC plus EP plus EK. Thus, the energy thus stored within a substance is called its internal energy. Internal energy change. If the internal energy of a system in the initial state is U1 and the final state it is U2, then the change in internal energy delta U is equals to U2 minus U1. Similarly, a chemical process, in a chemical reaction, if UR is the internal energy of the reactant and UP is the internal energy of the products, then the energy change accompanying the reaction would be delta U is equals to UP minus UR. The internal energy of a system changes when heat passes in or out of the system, work is done or by the system, matter enters or leaves the system. Internal energy is as a state function. Internal energy is a state function because it depends only upon the state of the system and it is independent of the method by which this state has been attained. For example, 1 mole of CO2 at 300 Kelvin and 1 atmospheric pressure will always have the same internal energy irrespective of the fact that it has been brought to these conditions under 500 K and 5 atmospheric pressure or from 1000 K to 10 atmospheric pressure. The internal energy is a state function which may be further explained as below. Considered a system containing certain amount of water in a thermos flask or in an insulated beaker. Let a change in the internal energy of the system by doing work called adiabatic work. The work can be done in the following two ways. By doing mechanical work, by rotating a small set of pedals, by doing electrical work again with the help of an emergent rod. So sign of U. Obviously, if U1 is greater than U2, means energy of reactant is greater than the product, the extra energy possessed by the system in the initial state would be given, and delta U will be negative according to the above equation. So units of U and E are 1 joule is equals to 10 raised to the power 7 ogs. Two most important things about the internal energies are following. The internal energy depends upon the quantity of the substance combined in the state, hence it is an extensive property. Second, the internal energy of ideal gases function of temperature only. Hence, in isothermal process, the temperature remains constant, so there is no change in internal energy, that is delta U is equals to 0. Second is work. As learned from lessons in physics, work is said to be have done whenever the point of application of force is displayed in the direction of the force. If F is the magnitude of the force and dl is the displacement of the point of application in the direction in which the net force acts, then the work done by the system is W is equals to F into dl. So work done is equals to A into two types of main the thermodynamics described as below. Electrical work. The generalized force is EMF and the generalized displacement is quantity of electricity flowing through the electricity. Hence, electrical work done is equals to EMF into quantity of electricity. Work of expansion or compression or pressure volume work. This type of work is involved in the system consisting of gases. This is the most important form of work used in the study of thermodynamics. It is the work done when the gas expands or contracts against the external pressure. It is a kind of mechanical work. The expression for such a work may be derived as follows. Consider a gas enclosed in a cylinder filled with frictionless piston. Suppose area of cross section of cylinder is A square centimeter. Pressure on the piston is P. Distance through which gas expands dl. Then as pressure in force per unit area. Then force acting on the piston is equals to P into A. Work done by the gas force into distance, that is equals to F into dl, where F is equals to P into A into dl. The gas expands from initial volume to initial volume V1 to final volume V2. Then the total work done by the is system is W is equals to P external into delta V. Sign of W and general expression for W. According to the latest SI conversion, W is taken as positive if work is done on the system, that is for compression, and it is taken as negative if work is done by the system, that is work of expansion. Hence, the general expression for work done is written as W is equals to minus P external delta V is equals to minus P external delta V2 minus V1. Units of W are 1 joule is equals to 1 Newton meter is equals to 1 kg meter square per second square. However, work done in isothermal reversible expansion of an ideal gas. Now we will calculate the formula for this and we will get W is equals to minus 2.303 nRT log V2 minus V1, or from Boyle's law we can also write W is equals to minus 2.303 nRT log P1 by P2. The negative signs indicates works of expansion. The same formula will be applied for the work of expression, because in that case V1 is greater than V2, so that log V2 by V1 is negative, hence the value of work will be positive. Difference in the work done in reversible expansion and irreversible expansion. In the reversible expansion of gas, the external pressure is only infinite, similarly less than the internal pressure at each stage. Hence, the expression for the work done is equals to minus P internal into delta V. This equation is further modified given below. In the reversible expansion, internal pressure is much different from external pressure. For example, if internal pressure is much greater than external pressure, then as the expansion takes place against internal pressure irreversibly, then the work done will be W is equals to minus P external delta, which is we explained below. Note that in reversible expansion, external pressure remains constant, but in reversible expansion, external pressure has to decrease continuously so as to remain infinitesimally smaller than the pressure. Now, reversible work of expansion is the maximum work. Free expansion of an ideal gas, expansion against vacuum, we will get W is equals to minus P external delta V, where work is equals to 0, so delta V is equals to also 0. Now next our next topic is first law of thermodynamics. It states that energy can neither be created nor be destroyed, but it can be converted into from one form to another form. Here are the justification of the first law of thermodynamics. So the energy is conserved in one form to another through one form of energy may be changed into other form. It is impossible to construct a perpetual motion machine, that is a machine which produces continuously without consuming energy. So here we will do mathematical formulation of the first law of thermodynamics. Suppose the initial energy of the system is U1. If it absorbs heat Q, its internal energy will be U1 plus Q. If further work is done on the system, the internal energy will further increase and become Q1 U1 plus Q plus W. Let us call its final internal energy U2, then U2 is equals to U1 plus Q plus W. So delta U is equals to Q plus W. This equation is the mathematical formulation of the first law of thermodynamics. If work is done is the work of expansion, then P is equals to minus P delta V, where delta V is the change in the volume and P is the external pressure. Then equation 1 can be written as Q is equals to delta U plus P delta U plus P delta V. Two interesting results follow from the mathematical formulation of first law of thermodynamics are under. First, neither Q or W is a state function, yet the quantity Q plus W is equals to delta is a state function because delta is a state function. Second, internal energy of an ideal gas is a function of temperature. Hence, for an ideal gas undergoing an isothermal change, delta U is equals to 0. Hence, Q is equals to minus W, that is the heat absorbed by the system is equal to the work done by the system. Next is enthalpy, that is another useful state function. The term initial internal energy has been already explained. Another important aspect of energy change follows from the first law of thermodynamics, according to which Q is equals to delta U plus P delta V. If the process is carried out at constant volume, then delta V is equals to 0. So the above equation reduces to QV is equals to delta U, where subscript V indicates constant volume. Hence, internal energy is the heat absorbed or evolved at constant volume. It may be mentioned that for the delta U is a state function, therefore Q is a state function. If a process is carried out constant pressure, as usual in the case because most of the reaction are in open vessel to atmosphere, so W is equals to V delta V. V is the increase in the volume and P at constant pressure. According to first law of thermodynamics, we know Q is equals to delta U minus W if Q is the heat absorbed by the system and delta U is the increase in internal energy of the system and W is the work done by the system. Under condition of constant pressure, putting W is equals to minus P delta V and representing the heat absorbed by QP, we get QP is equals to U plus P delta V. Suppose when the system absorbs QP joules of heat, its internal energy increases from U1 to U2 and the volume increases from V1 to V2. Then we have delta U is equals to U2 minus U1, delta V is equals to V2 minus V1. So putting this equation in equation third, and we will get QP is equals to U2 plus P V2 minus U1 plus P V1. Now as U, P and V are the functions of state, therefore the quantity U plus PV must also be a state function. The thermodynamic quantity U plus PV is called the heat content or enthalpy of the system and it is represented by the symbol H. Then the enthalpy may be defined mathematically by the equation H is equals to U plus PV. If H2 is the enthalpy of the system and in the final state and H1 is the value of initial state, then H2 is equals to U2 plus PV2 and H1 is equals to U1 plus PV1. So putting these values in equation number 6, we will get QP is equals to H2 minus H1, that QP is equals to delta H, where delta H is equals to H2 minus H1 is the enthalpy change of the system. Hence, enthalpy change of a system is equal to the heat absorbed or evolved by the system at constant pressure. So delta H is equals to delta U plus Q delta V. Now here is the another definition of enthalpy change. Now we will do exothermic and endothermic reaction. Exothermic reaction. These are those reactions which are accompanied by the evolution of heat. The quantity of heat produced is shown along the products with the plus sign. A few examples of exothermic reactions are C plus O2 is equals to CO2 plus 393.5 kilojoule energy is released. Similarly, C4H10 plus 13 by 2 O2 is equals to 4 CO2 plus 5 moles of water plus 2658 kilojoules of energy is released during this reaction. Now next is endothermic reaction. Those reactions in which heat is absorbed is called endothermic reaction. Although the heat absorbed can be written with the plus sign along with the reactants, however, it is usually along the products with the minus sign. A few examples of endothermic reactions are given below. N2 plus O2 is equals to 2NO minus 180.7 kilojoule. H2 plus I2 is equals to 2HI minus 52.5 kilojoule of energy. Exothermic and endothermic reaction in terms of delta H. The enthalpy change accompanying action is given by delta H is equal to heat of the contents of products minus heat contents of reactant, that is HP minus HR. A reaction is exothermic. Then heat is given out in the reaction if total heat content of reactant is more than that of product, that is HR is greater than HP. But if it is so, then according to above equation delta H will be negative. Hence delta H is negative for exothermic reaction and delta H is positive for the endothermic reaction. Graphically, the exothermic and endothermic reactions are also represented by this. A branch of chemistry which deals with the heat changes accompanying chemical reactions is called the thermochemistry. Next is different types of heat enthalpies of a reaction. Heat of reaction or enthalpy of a reaction is a general term used for the heat change accompanying any reaction. However, depending upon the nature of the reaction, the enthalpy of reaction is named accordingly, that is enthalpy of combustion, enthalpy of neutralization, etc. Similarly, depending upon the type of reaction involving a phase change, fusion, vaporization, sublimation, etc. The enthalpy change involved is named according, that is enthalpy of fusion, enthalpy of vaporization, etc. So first is enthalpy of combustion. The enthalpy of combustion of a substance is defined as the heat change when 1 mole of the substance is completely burnt or oxidized in oxygen. That means CH4 plus 2 of O2 is equals to CO2 plus 2 of water. And then enthalpy of combustion for this is minus 894.4 minus 890.4 kilojoule per mole. This reaction shows that 890.4 kilojoule of heat is produced when 1 mole of methane is completely burned. Hence, enthalpy of combustion of methane is 890.4 kilojoule per mole. Standard enthalpy of combustion is the amount of heat evolved when 1 mole of a substance under standard conditions, that is 298 Kelvin temperature, 1 bar atmospheric pressure, is completely burned to form the products also under standard condition. It is represented by delta CH naught. The standard enthalpy of combustion of butane is minus 2658.0 kilojoule mole. Calorific value of food and fuels. Just as the fuels like coal, kerosene oil, gasoline, diesel oil, etc., they burn to produce energy for the running of machines. Similarly, for the working of human machine, wheat, carbohydrates, fats, etc., in the form of food. The carbohydrates are first decomposed in our body by the enzymes from glucose, which then undergoes oxidation by the oxygen that we inhale to produce energy. And the energy that is produced is minus 2840.0 kilojoule per mole. The oxidation reaction is usually called combustion of food. Different fuels and food produce different amounts of heat or combustion. They are usually expressed in terms of their calorific value, which is defined as the calorific value of a fuel or food is the amount of heat in the calories or joule produced from complete combustion of 1 gram of the fuel or the food. A normal person needs about 300 kcal per day. The food consists in carbohydrates, oils, fats, vitamins, proteins, minerals, salts, etc., which provides the necessary calories called a balanced diet. Next is enthalpy of formation. The enthalpy of formation of a substance is defined as the heat change, that is, heat evolved or absorbed when 1 mole of substance is formed from its elements under given conditions of the temperature and pressure. It is usually represented by delta FH. The condition of temperature and pressure usually chosen are 298 Kelvin and 1 bar atmospheric. They called standard state. The enthalpy of formation under these conditions is called the standard enthalpy of the formation. For example, C plus O2 is equals to CO2. Then enthalpy of formation is equals to minus 393.5 kilojoule per mole. When 1 mole of CO2 is formed from its element, C and O2 whole substance being taken standard value, 393.5 kilojoule of energy is produced. Hence, standard enthalpy of formation of gaseous CO2 is 393.5 kilojoule per mole. Next is importance of standard enthalpies of formation. Knowing the standard enthalpies of formation of the different compounds involved in a chemical reaction, the standard enthalpy change of given reaction can be calculated. So delta HF is equals to sum of the standard enthalpies of formation of product minus sum of the enthalpies standard enthalpies of formation of the reactants. So next is enthalpy of neutralization. The enthalpy of neutralization of acid by base is defined as the heat change when 1 gram equivalent of the acid is neutralized by the base. The reaction being carried out in dilute aqueous solution. The enthalpy of neutralization of a base by an acid is defined in a similar manner. For example, when 1 gram equivalent of HCl is neutralized by NaOH or 1 gram equivalent of NaOH is neutralized by HCl, both solution being dilute and aqueous, 57.1 kilojoule of heat is produced. Thus, we came here, right? Hence, enthalpy of neutralization of HCl with NaOH or NaOH with HCl is 571 kilojoule. So our next is enthalpy of solution. The enthalpy of solution of a substance in a particular solvent is defined as the enthalpy change when 1 mole of substance is dissolved in a specific amount of the solvent. However, if such a large volume of solvent is taken, the further addition of the solvent does not produce any more heat changes. It is called the enthalpy of solution at the infinite dilute. Next is Hess law of constant heat summation. G.H. Hess, a Russian chemist in 1840, gave a law about the heat of reactions on the basis of experimental observation. This law is known after his name Hess law. It states that the total amount of heat evolved or absorbed in a reaction is the same whether the reaction takes place in one step or in a number of steps. In other words, the total amount of heat change in a reaction depends only upon the nature of the initial reactants and the nature of the final products and is independent of the path or the manner by which this change is brought. Basis of Hess law. Hess law follows from the fact that enthalpy is a state function. Enthalpy change depends only on the initial state and the final state and does not depend upon the path followed. Example, when carbon means graphite bonds to carbon dioxide directly in one step, 393.5 kilojoule mole of heat is produced. If carbon bonds to form carbon monoxide first, which then turns to form carbon dioxide, the heat involved in both the steps is remains the same. Second is the sulfur bonds to form S2O3 directly in one step and the heat is minus 395.5 kilojoule. Sulfur may changes to SO3 in two steps, then a heat change will be also minus 395.4. Now suppose the same reaction taking place in a three step. A is converted into B, then B is into C and C into D. Suppose the heat evolved in three steps are Q1, Q2 and Q3 joules respectively. The total heat evolved Q1, Q plus Q2 plus Q3 is equals to Q dash. According to Hess law, we must say Q is equals to Q dash. If Hess law were not correct, then either Q dash is greater than Q or Q dash is less than Q. Suppose if Q dash is greater than Q, this means that we go from A to D in number of steps. The heat evolved is more than the heat absorbed when we return from D to A directly in one step. Remember that for the direct process, A is converted into D. Q joules of heat is evolved. So for the reverse process, which D is converted into A, Q dash joules of heat will be absorbed. Then when the cyclic process is completed, then Q minus Q dash joules of heat is produced. Thus, by repeating the cycling process a number of times, a large amount of heat can be created. This is, however, against the law of conservation of energy. Hence, Q must be equals to Q dash. That is, Hess law must be correct. Application of Hess law. The most important application of Hess law is in the calculation of the heat changes for those reactions for which experimental determination is not possible. The calculation based upon the following sequence of Hess law. The thermochemical equations can be treated as algebraic equations which can be added, subtracted, multiplied or divided. And the few applications of Hess law are below, that is calculation of enthalpy of formation, enthalpy of neutralization, enthalpy of fusion, etc. Now here are the limitation of first law of thermodynamics. A major limitation of first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of energy involved, but it provides no information commenting the spontaneity or feasibility of the process, whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold end to hot end or not. All these false is that if this process occurred, the heat energy gained by one and would be exactly equal to that of the laws to the other end. Similarly, the first law does not tell whether a gas can diffuse from low pressures to high pressure or water can itself run unfilled, etc. The answers to the above questions are provided in the second law of thermodynamics. However, we are take up different statements of second law of thermodynamics later. It is important to know that we understand by spontaneous process and also introduce to more thermodynamic quantities, namely entropy and gas free energy. Spontaneous and non-spontaneous process. Dissolution of sugar in water at 25 degrees Celsius. Here, this is the example of spontaneous process. Burning of coal in air oxygen. This is also the example of spontaneous process. The first process takes place by itself, although it may be slow. The second process cannot take place by itself. It needs initiation, that we have to bring a flame near to the coal to start its burning. But once it starts burning, it goes on by itself without the help of any external agency. Both the above processes are spontaneous process. Hence, a spontaneous process may be defined as a process which under some given conditions may takes place by itself or by initiation independent of the rate is called a spontaneous process. It may be noted carefully that a spontaneous process does not mean that the process should instantaneous. In fact, the rate of the process may vary from extremely slow to extremely fast. For a more clear understanding, a few more examples of the spontaneous process are as follows. A. Examples of process which takes place by themselves. Dissolution of common salt in water. Evaporation of water in open vessel. Flow of heat from cold end to cold, from hot end to cold end, or from a hot body to cold body, that is cooling down of the tea. Flow of water down a hill, combination of H2 and Nitrogen to form HI. Combination of nitric acid and oxygen to form nitrogen dioxide. B part is examples of processes which takes place on initiation. Lighting of candle involving burning of wax. Heating of calcium carbonate to give calcium oxide and carbon dioxide. Reaction between methane and oxygen to form carbon dioxide and water. On the other hand, a process which can neither take place by itself nor by initiation is called a non-spontaneous process. A few examples of the non-spontaneous process in everyday life are as follows. First is flow of water up a hill. Second, flow of heat from a cold body to hot body. Third, diffusion of gas from low pressure to high pressure. Fourth is dissolution of sand in water. Are driving force for a spontaneous process. After having learned what we mean by spontaneous process, the next question that arises in our mind, why some processes are spontaneous? Obviously, there must be force which drives the process or a reaction in a particular direction. This force which is responsible for the spontaneity of a process is called the driving force. Let us now see what is the nature of the driving force. First is tendency for minimum energy. It is a common observation that in order to acquire maximum stability, even system needs to have minimum energy. For example, a stone lying at a height has a tendency to fall down, so as to minimum potential energy. Water falls down a hill to have minimum energy. A wound watch spring has tendency to unwind itself to decrease its energy to minimum. Thus, all the above processes are spontaneous because they have a tendency to acquire minimum energy. All these reactions are accompanied by evolution of heat. In other words, the heat content of the product is less than those of reactant. Thus, again, we may conclude that these reactions are spontaneous because they are accompanied by the degrees of energy. Hence, one may conclude that a tendency to attain minimum energy, that is a negative value of enthalpy, change delta H might be possible for a process or a reaction to be spontaneous or feasible. Now there are the limitations for the criterion of minimum energy. First, a number of reactions are known which are endothermic, for which delta H is positive, but still they are spontaneous reaction. That is evaporation of water or melting of ice, dissolution of salts like NH4, Cl, KCl, decomposition of calcium carbonate on heating, decomposition of N2O5 at room temperature. Second, a number of reactions are known for which delta H is zero, but they are still spontaneous. That is reaction between acetic acid and ethyl alcohol. Expansion of ideal gas into vacuum is also the example. Even those reactions for which delta H is negative rarely proceed to complete even though delta H remains negative throughout. Fourth is reversible processes do not occur. Hence, it may be concluded that energy factor and enthalpy factor cannot be the criteria for the proceeding, the spontaneity or the feasibility of the process. So, thus, some for more factor be involved. This factor is a tendency for maximum randomness, and the maximum randomness is called the entropy. So, thank you. This is all about this chapter.